Okay, guys, so today we're going to be talking about polynomial functions of a higher degree. So yesterday we talked about quadratic functions. Now we're going to talk about functions that have a higher degree than 2. Because quadratics, of course, have a degree of 2. So we're going to talk about ones today that are higher than 2. So first, let's talk about polynomial functions of higher degrees. When you see their graph, a couple things that they have to have are they have to have smooth, continuous curves. Okay, so for example, this right here is obviously it's a continuous line. There's no breaks in it. An example of something that would not be a polynomial function would be something like this. You know, one of our piecewise functions, that is not a polynomial function because it's not continuous. Another example is it's got to be smooth. So notice that all of the curves on this graph are very smooth, rounded curves, as opposed to a function like an absolute value function that has a point. That is not a polynomial function because it doesn't have a smooth curve. It's got a point to it. So on graphs, all polynomial functions should have smooth, rounded curves like those two graphs on the left. Now, when you're looking at polynomial functions, we can do what's called a lead coefficient test. Because for any polynomial function where a is the lead coefficient, then it tells us something about the graph. Now, the lead coefficient is the number in front of the x that has the highest exponent. So, for example, right here, okay, right here, the lead coefficient, even though 3 is the first one, that's not the lead coefficient. The lead coefficient right here would be -4 because it's the coefficient on the x that has the highest exponent. Its exponent is 4. So because it's the highest degree term, that would be our lead coefficient, -4. Okay, so that's just an example of, you know, what the lead coefficient is, just to make sure we understand a lead coefficient. So when we look at a lead coefficient, okay, two situations could happen. Either the degree is even, so it's like x squared, x to the 4th, x to the 6th, or the degree is odd, x to the 3rd, x to the 1st, x to the 5th, all those odd numbers. So when the degree is even, if a, the lead coefficient, is positive, more than 0, okay, when it's even, then your end behaviors, what we know is the end behaviors are going to go up and up. Okay, the ends of your polynomial function, the ends of the graph, are going to end going up and up. There could be all kinds of stuff in here, curves, whatever, but we know that it's going to end going up and up on the ends of the graphs, okay? Now, the notation that you'll see used sometimes for this is you'll see as x approaches -infinity, which just means the left, right? X -infinity is over here. So as x goes to -infinity, f of x goes to positive infinity, meaning the y values go up. And as x approaches positive infinity, f of x approaches positive infinity, which just means as x gets bigger, y is going to get bigger. Y is going to go towards infinity. So the second situation is if the degree is even and a is less than 0. If a is negative, your end behaviors are both going to go down. So when it's even means they're going to go the same direction. Okay, so if it's even and positive, they both go up. If it's even and negative, they both go down. Alright, so on right here, the notation we could say, you'll see sometimes is as x approaches -infinity and as x approaches positive infinity, f of x approaches -infinity, which means it goes down. Okay, this is just a funky way of saying as we go left, the graph goes down, and as we go right, the graph goes down. Okay, so the other situation that could arise is you could have an odd degree. So if the highest exponent on the polynomial function is an odd number, and a is greater than 0, your end behaviors are going to do this. On the left side, it's going to go down, and on the right side, it's going to go up. So you could have all kinds of curves and stuff in here, but the way the graph ends is down on the left and up on the right side. Now, the way we would write that is as x approaches -infinity. Of course, that means going left. Then f of x is obviously approaching -infinity because it's going down. And as x approaches positive infinity, meaning as we go to the right, f of x is approaching positive infinity, or going up. So it's saying on the right it goes up, on the left it goes down. And the last situation, obviously, is if it's odd and a negative lead coefficient, it's going to go up on the left and down on the right. Okay, and the way that I kind of remember this is just by the slope, right? A positive slope, A is positive, as a positive slope should go uphill. When A is negative, like a negative slope, the graph should go downhill. So, of course, right here we'd say as x approaches negative infinity, meaning as we go to the left, f of x is going to approach positive infinity, which means the y is going to go up. And as x approaches positive infinity, f of x is going to approach negative infinity, meaning as we go towards the right, to where x is positive, f of x is going to go to the negative, or down. Okay, so we can use this knowledge of end behaviors to determine the lead coefficients of functions. So looking at this function right here, we want to use the lead coefficient test to describe the right hand and left hand behavior of the graph. So what we want to look for first is the degree. We see our degree is odd. Well, when the degree is odd, we know that the end behaviors are going to be different. Right? One's going to go down, one's going to go up. Whenever it is odd and the lead coefficient is negative, like in this situation, okay, since it's going to be different, we know since it's negative, it's going to be like a negative slope. So if it's a negative slope, that means it's going to be going up on the left and down on the right, because it's got to start up high and come down low to be a negative slope. So describe the end behaviors, we could say it goes, you could say it goes up on the left and down on the right. Or you could use the notation like we used on the previous slide. Either way is fine. All right, so I'm going to go ahead and pause the video. You guys give these two down here a try. Okay, so for A, we got an even degree. Right, the degree is 4. So because we have an even degree, we know that the end behaviors are going to go the same direction. And it's positive 1 out here. So positive means they're both going to go up. So up on the left and up on the right. All right, right here we've got odd, which means they're going to go different directions. Since it's positive, it'll be like a positive slope. So that means it's going to go down on the left and up on the right to be a positive slope. All right, let's move on. So let's find real zeros. Okay, zeros are essentially x-intercepts, or you can think of zeros, just plug in 0 for y and see where is y 0, or f of x. So that's what we're going to do right here. We're going to make f of x 0. The 0 of a function is just what makes that function equal to 0. So now to do this, we got to factor. So first of all, the first step you always use when factoring is to find the greatest common factor. What's the biggest thing that all three of these terms have in common? Well, they don't have a number in common because x cubed and x squared don't have a number, but they all have an x. So we can take out an x from all three of them. Then in parentheses, we need to put what's left over. So if I take x from x cubed, that leaves an x squared. If I take an x away from x squared, that leaves x. If I take an x away from the 2x, it just leaves the 2. All right, so now I've factored out my greatest common factor of x. Now we got to try to factor what's left. We got a trinomial. So we talked about how to factor trinomials. I'll put a 2 in the top. I'll put the minus sign right here in the middle, and then the coefficient that's in the middle right here, which is a 1 in the bottom. All right, so my question is, what multiplies to be 2 and subtracts to be 1? Well, obviously that's 2 and 1. So I'm going to rewrite everything else so far. Put x with a 2 in one parenthesis and x with a 1 in the other. Now our signs, how do we determine what signs to put? We're going to put this sign how many times? The other sign tells us, just once. If we can only use that minus sign once, we put it on whichever number is bigger. So I'm going to put a minus on this one and a plus on the 1. If the minus in front of that 1x was a plus, then we would put a plus on the bigger number, put the plus on the 2. All right, so now we've got it factored, and we can't factor anymore. So what you do now is every factor you have that has a variable in it, you set each of those equal to 0. So I'm going to set x equal to 0. That's one factor. My other factors are x minus 2 and x plus 1. So I set all these equal to 0 and solve them. Well, this one's already solved. Add 2, so x equals 2. And subtract 1, so x equals negative 1. So those are my zeros. Those are my 3 real zeros. I knew I was going to have 3 zeros because it was a cubed function. Okay, the exponent tells you how many total zeros you are. They might not all be real zeros, okay, but in this situation, all 3 of them were real zeros. Some of them could be imaginary. Right here, all of them are real. So go ahead and pause the video, and you guys try the one down here at the bottom of the screen. Make sure when you factor out the biggest thing possible. All right. And also you'll want to factor out the negative with the number 2. Right here, we factor out a negative 2x squared as our greatest common factor, which leaves x squared minus 1. And now when we factor x squared minus 1, notice there is no middle term, but it's understood it's 0x, right? It's 0x. So you say what multiplies to be 1 and subtracts to be 0. Well, obviously those numbers are 1 and 1. So you put a 1 in one parenthesis with x, 1 in the other parenthesis, and you say, well, what signs do we use? Well, we use a plus in one of them and a minus in the other. That way they cancel to give us 0. Or you can just think of it as a difference of squares, and you factor difference of squares by doing a plus b and a minus b, if you remember that. If you don't remember that, you can feel free to ask me about it. So that's some algebra stuff that you should have been taught at some point. So then you set each of those 3 factors equal to 0. Negative 2x squared equals 0. Divide by negative 2 and take the square root. You get x equals 0. Add 1 for x minus 1, get 1. Subtract 1 and get x equals negative 1. So those are your 3 zeros. You also had to find the relative extrema. So those are your maximums and minimums. So I'm going to have to zoom in right here on the graph to see them. All right, and we all remember how to do this. Right here, you've got 2 maximums, right? You've got a maximum here, and a minimum here. So you have to calculate, find the maximum, left bound, right bound, enter. So the maximum right there is 0.5, a half. And then the other one's also going to be a half. And then you can calculate your minimum, left bound, right bound. And your minimum is, when you get this on the calculator, guys, 8.42, e negative 12. That e negative 12 means move the decimal 12 places this way. Okay, the calculator, it has to kind of approximate and use algorithms to figure it out. It's actually 0. The minimum is 0, but it's thinking doing a whole formula to try to figure it out. So that's why it's approximating it to a really small decimal. So those are your extrema. Now notice something right here. Okay, notice that at the 0, 1. Okay, we got x equals 1 right here, and x equals negative 1. Those, the graph just crossed through the x-axis. But where x equals 0, notice it hits and bounces off. Okay, the reason it does that is because we really got 0 as one of our zeros twice. Because when I do the square root, I really need to do plus minus. So really I got 0 as an answer twice. Anytime you have a number that's a 0 2 times for the same function, at that 0, it's not going to cross through the axis, it's going to bounce off of it, like it does right here. It just comes down and then hits it and bounces off. All right, so that's something to understand about zeros when you start having multiple zeros of the same value. Okay, so let's go on to example 3. I want to find a polynomial function with the zeros at 3, 3, and negative 1/2. So we're actually going to write the function this time. And there's a lot of different answers, but there's a basic process to figure this out, to figure out just a real basic one. So what you want to understand is when you have a 0, okay, any 0 you have, you can write a factor for that 0 by just doing x minus that 0. So I'm going to write x minus 3, and I'm going to write one for the other 3, x minus 3, and then I've got a minus 1/2, so I'm going to write x minus negative 1/2, which really makes x plus 1/2. Okay, so when I write all these factors, one for each 0, now to write the function, I'm just going to multiply all these together, and it'll give me a function that will have those 3 zeros. So I multiply x times negative 3, it's x squared minus 3x, minus 3 times both, it's minus 3x again, and plus 9. And then I'm going to combine my like terms. So I got x squared minus 6x plus 9. And then I've got to distribute all 3 of these to both terms of the binomial. So I got x squared times x. And that gives me x cubed. X squared times 1/2 is 1/2 x squared. Right, and then I've got to do negative 6x times x, negative 6x squared. Negative 6 times 1/2 is negative 3x. 9 times x, 9x. And then 9 times 1/2 is 9/2. And I just got to go through and combine like terms. So I got 1x cubed I've got a half x squared minus 6x squared. So that would be minus 5.5 x squared, or minus 11 halves x squared. Minus 3x plus 9x is 6x. And I've got plus 9 halves. So this is a function that would give me a zero, give me a function that has all three of those as zeros. Now, one thing that you could do right here to clean up all this fraction stuff is whenever you have a fraction like this as a zero, you can use this, or something that makes it easier is make the function, move this denominator right here in front of the x and use this as a factor. Okay, because that will also give you a zero of negative 1/2. So it would be cleaner and not have all these fractions if we plug 2x plus 1 in instead of x plus 1/2. So do that instead of this, and that'll keep you from having to worry about all these fractions. All right. So you guys go ahead and try the next one. This one doesn't have a fraction, but just be aware when you have a fraction like this, once you set it up, move the 2 over in front of the x, okay, or whatever your denominator is. That way you don't have to worry about fractions. All right, so give this next one a try. So right here you can see the work I did. Subtracted all my zeros, and then distributed, it's most distributed property, and the answer you should get is x cubed plus x squared minus 6x. Let me know if you have any questions about that. I'll come around and help you. All right, last example we need to do is how to sketch a graph. So first thing we want to determine is the end behaviors, okay? So just what would the end behaviors of this be? We got an even function, even degree, and it's odd, or it's positive in front. So since it's even, we know they're going to go the same direction, and it's positive, so we know they're both going to go up. Okay, so I'm just going to put arrows up here just to remind myself that I should get a graph where the end behaviors go up because of the lead coefficient test. All right, second thing we're going to do is find the zeros, just like we've been doing. So I'm going to plug in 0 for f of x and then solve it for x. So let's factor out what we greatest common factor. I can't take a number out of 3 and 4, but they do all have an x cubed. So I'm going to remove the x cubed. That's going to leave 3x when I take 3 x's away. And then I'll take 3 x's away from minus 4x cubed, it's just going to leave the minus 4. That's as much as I can factor it. So now set each factor equal to 0 that has a variable in it. So right here I'm going to add 4. So 3x equals 4. And then divide 3. So x equals 4/3. So I know I'm going to have an x-intercept somewhere at 1 1/3. So right around in there. All right, then to solve the other one, I get rid of a cube, so I need to take the cube root. So x equals the cube root of 0, which is 0. All right, now this 0 right here of 0, it's a 0 3 times because it was x cubed equals 0.
Pardon the interruption. Now I'll field.
All right, so this x equals 0 is going to be a 0 3 times because of the x cubed. All right, so just like we talked about a second ago, when it's a 0 twice, it's going to bounce off the graph. Well, whenever a 0 is a 0 3 times, the graph goes through it, but it's going to kind of flatten out at it. Okay, so if this is a 0, it's not just going to go straight through. That's what it would do if it was just a 0 once. When it's a 0 3 times, it's going to come up, it's going to kind of flatten out, and then it's going to go up again. All right, so we should expect it to do that where x is 0, which is our other 0. All right, now the next thing you want to do is just plug in some other points to figure out the behavior of the graph. You know that it's going to come down from somewhere over here, all right, but we got to figure out where those points are going to be. So if we plug in 2, plug in something in between our 2 zeros to figure out what it does in there. I'm not going to plug in, 1, plug in a half, all that stuff to figure out what those functions are going to do at those points, right, to give us an idea of the graph. Okay, whenever we plug in some more of the points right here, you guys can do that. You know how to plug in points. We see that we're going to get a function that has, I believe it's going to be, let's see, right down here. All right, so we knew it was going to start up to the top. So we see it's going to come down and go through that point because it's just a 0 once, right? This just was a 0 one time. So it's going to come straight through it. It's going to turn out, and it's probably come up here and level out a little bit like this, and then go up. Because we said at this 0, since it's a 0 3 times, it's got to kind of flatten out at it instead of going straight through it. So it's going to come straight down through, come down through the point. A couple of these other points we graph, you guys can plug in values and see what you get to find some other points out here. I'm not going to take time to do that, but that's how you can find some other points to help you out on your graph. So if you know the end behaviors and you know the zeros, once you find those, then just plug in some other points to get an idea of what the shape of the graph is going to look like, and you can you can draw that graph and have a good little sketch that is pretty accurate. All right. So go ahead and pause it and try the last problem on your own. Okay, so right here, first thing we need to determine is what's the end behavior. We notice that the degree is odd. So with an odd degree and a negative coefficient out front of -2, we know that it's going to go opposite directions, the end behaviors will, and negative, so it'll be a negative slope. So it's going to go up on the left and down on the right somewhere. All right. So now let's figure out what are the zeros. So we set the function equal to 0. Alright, and we need to factor. So what we should try to factor right here is take out the negative, but also take out a half to get rid of that fraction. So if we take out -1/2 and an x, because they all have an x in common, then in parentheses, when you divide 2 by a half, it's going to make it 4. Right? So all of my coefficients now are going to be twice as big when I divide out a half. Of course, the negative is going to change all the signs, so it's going to be minus, and 6 is going to become a 12. It's just 1x now because I took an x out front. And then I take out a negative, so it makes it positive. I took out the half, so that just leaves 9. And I took away the x, so it's just 9 by itself. So now, sorry, this should be a squared. So now I've got to factor 4x squared minus 12x plus 9. Now we haven't talked about this, how to factor a trinomial when it's got a coefficient right here on your x squared. So what you're going to do is something I call slide and divide. You're going to slide it over and multiply it by the number at the end and make it 36. Then do your x box. So what multiplies to be 36 and adds up to 12? That'd be 6 and 6. So we're going to have x and 6, x and 6, and then a minus is going to go on both of the numbers. Of course, still have a -1/2 x. Now we slide and divide. So we slide the 4 over, but then you got to go back after you factor and divide by 4. So I'm going to divide both of these 6's by 4 because you got to undo that slide that you did earlier. Okay, so now you've got 6 over 4, which is really 3/2. Right? And so now we can set each of those factors equal to 0 and solve. So I'm going to say -1/2 x equals 0 and x minus 3/2 equals 0. Notice I've got that same factor twice, so I don't need to set it equal to 0 both times. So add 3/2, so x is going to equal 3/2, and then divide by -1/2, so x is going to equal 0. Notice that this 0 is just 1, there's just one of them, right? But 3/2 is a 0 twice. So we say it's got a multiplicity of 2, meaning it's a 0 twice. So we're going to have an x-intercept at 0, an x-intercept at 1.5. But this one is a multiplicity 2. So remember, when it's multiplicity 2, we expect the graph to bounce off of it. Alright, so not just go through it, but we expect it to bounce off of it. So since it's going to start up high, we can graph some points, somewhere, plug in some of these x values to find some other y values. But we know it's going to start up high, it's going to come down, and because 0 is just a 0 one time, we know it's going to pass through that 0. Alright, now to get to the other 0, it's going to have to turn around at some point. You can graph points in between 0.5 to 1.5 to figure out where it's going to turn around at and all that stuff. So it's going to turn around, but then when it gets here, because this has a multiplicity of 2, it's not going to pass through it. It's going to try and bounce off of it and come back down. And then it's going to finish going down somewhere. Again, we don't know where those points are at, but you can plug in other x values, 3, 4, all these points in here to figure out where is this line going to be. Maybe it's up here, maybe it comes down steeper down here somewhere. So that's just all depending on what values you get whenever you plug in different x values. But we do know it's going to have the end behaviors up on the left, down on the right, and it's going to go through the point 0, and it's going to bounce off of the 0 at 3/2. Okay, so appreciate your all's attention. Let me know if you have any questions, and go ahead and do these practice problems right here, and let me know if you need any help.